Hello and welcome to lecture 17 of our course on stochastic modeling of biological processes. In this lecture, we will continue in our discussion of reaction-diffusion modeling. In our last lecture, we started with the corresponding deterministic reaction-diffusion partial differential equations, which give the time evolution of concentrations of chemical species, Ci, and include terms describing both diffusion and reactions. Then we discussed compartment-based modeling, which is a relatively straightforward approach to implement in a computer, because it uses the methodologies for chemical reaction systems which we developed in Chapter 1. We divide the domain into compartments and describe the state of the system by the number of molecules in each compartment. Molecules that are in the same compartment are indistinguishable, and we postulate that chemical reactions can only happen when the reacting molecules are in the same compartment. While this model is easy to implement, some important questions were not addressed in our previous lectures. One of them is, what is the appropriate choice of the compartment size H? In this video, we presented a linear model, for which we derived the equations for the average number of molecules in compartments. Passing to the limit H goes to 0, we derived the corresponding deterministic reaction-diffusion equation, which could also be viewed as an equation for the probability distribution function of a single molecule. That is, the exact description which we are attempting to approximate using the compartment-based approach. Consequently, for reaction diffusion systems involving only zero-order or first-order chemical reactions, we can increase the accuracy of stochastic simulations by decreasing the compartment size H. The situation is much more delicate when the system involves second-order or higher-order reactions. In that case, diffusion is still modeled more accurately when the compartment size H is decreased, but the second-order reactions are modeled less accurately as H is decreased, so that we lose accuracy if we choose H too small. You can intuitively understand this problem when you look at this schematic. There are 18 red molecules in 5 compartments. If I use a smaller compartment size, say H is 10 times smaller, then I will have 50 compartments. Since there are only 18 molecules, there will be at least 32 compartments which are empty, and the remaining compartments will often only contain one molecule. In particular, no second-order reaction will occur until there are at least two molecules in the same compartment. In summary, if I decrease the compartment size H, then I increase both the jump rate between the compartments and the rate at which a pair of molecules in the same compartment can react. However, I will also decrease the chance that there are two reactants available in the same compartment. The choice of the compartment size H is discussed in more detail in section 6.4, which is not covered in our videos. Students interested in this topic can read about it in section 6.4. But in our lectures, we will instead look how we can reproduce this video using a molecular-based approach. The molecular-based modeling of reaction diffusion processes does not include any compartments. In this modeling framework, we instead calculate the trajectories of individual molecules. If there are any second-order reactions in the model, then we will postulate that they will happen with a certain probability when two reacting molecules are at a specific distance, called the reaction radius. Fortunately, our first illustrative example does not have any second-order reactions, so it is easy to implement. It is the model which we have already used in section 6.1, where we considered an elongated domain, a cuboid of length L and side H. Molecules diffuse and are degraded in the whole domain. Molecules are also produced in the red part of the domain, and there are initially no molecules in the system. In section 6.1, we presented the compartment-based model 6.1 to 6.3. To formulate it, we divided our computational domain into k compartments, little cubes with their edges of length h. We denoted by AI the number of molecules in the ith compartment. The compartment-based model was then written as a system of chemical reactions, including the chain of chemical reactions which we used for modeling diffusion in chapter 4. Degradation reaction corresponded to K degradation reactions, and the production was localized to red compartments. In section 6.2, we present the corresponding molecular-based model. It does not include any compartments, so I have removed compartments from my schematic here, and I added black dots, which schematically show that the molecule-based model will calculate trajectories of all molecules. To do that, we will use algorithm A8 to C8 from section 4.1, which I have included on this slide. Algorithm A8C8 calculates the position of the molecule at time t plus delta t from its position at time t using our computational definition of the corresponding stochastic differential equation. So we generate a normally distributed random number xi, which is multiplied by the square root of 2d times delta t to obtain the random displacement, which is added to the current position at time t. If the calculated position xt plus delta t is outside of the simulated domain, then we use reflective boundary conditions in step C8 to return it back to the domain. The algorithm A8C8 models diffusion with reflective boundary conditions, so I have temporarily removed in my schematic the red region. However, our goal is to describe exactly the same reaction diffusion process as in section 6.1, so we need to add the descriptions of corresponding reactions as well. The resulting stochastic simulation algorithm is presented as the SSA A17C17 on page 165. In the first step, we implement diffusion with reflective boundary conditions. For each molecule, we compute its x-coordinate at time t plus delta t according to the steps A8C8. The degradation of each molecule is implemented in step B17. For each molecule, we generate a random number R1 uniformly distributed in the interval 0, 1. If R1 is less than the probability of degradation, which is K1 times delta t, then we terminate the trajectory of the simulated molecule. The last step implements the production reaction with the help of two random numbers R2 and R3. The first one, R2, is used to decide whether another molecule should be introduced to the system. If this happens, then we use random number R3 to select the starting position of the new molecule in the red part of the computational domain. Some of you might have noticed that my algorithm uses the finite time step delta t, so its treatment of reactions is similar to the naive stochastic simulation algorithm which we have used in chapter 1 to motivate the Gillespie algorithm. The Gillespie algorithm is an event-based algorithm. It is more efficient than the naive algorithm. So as an exercise, you could think about designing an event-based version of algorithm A17C17. For example, instead of using one random number at each time step to decide whether the given molecule was degraded in step B17, we could instead only use one random number to calculate the time when the molecule will be degraded. In a similar way, we could also avoid using the time step delta t in the other steps of the algorithm to design a fully event-based algorithm, which could be more computationally efficient. The results of one realization of the SSA A17C17 are presented in figure 6.2. We compare them with the black line, which is the solution of the corresponding deterministic partial differential equation model, with zero flux boundary conditions, and the initial condition A at time t is identically equal to 0. This equation provides a very good description of the average behavior of our stochastic simulation algorithm. In fact, the black line is the exact description of the average behavior if we consider the limit of the time step delta t goes to 0. To visualize the computed results, we divide the domain 0L into 40 bins and we plot the number of molecules in each bin as the gray histogram. In this way, we can also directly compare figure 6.2 with figure 6.1, which was calculated for the compartment-based model in our last lecture. Considering the spatial histograms, the results calculated by one realization of the Gillespie algorithm are indistinguishable from the results calculated by the molecule-based model. Another simple reaction-diffusion model is presented in sections 6.3 and 6.5. We again consider the same elongated domain, cuboid of length L and side H. We consider two chemical species A and B that diffuse in this domain and are subject to 6 chemical reactions, which include production of B that is localized to this red region. The compartment-based model was presented in our previous lecture 16, where we apply the Gillespie stochastic simulation algorithm to the system of chemical reactions 614 to 618. In this lecture, we will discuss the corresponding molecule-based model, which is included as the stochastic simulation algorithm A18 to E18 on page 176. Since there are no compartments in the formulation of the molecule-based model, I have replaced them in my schematic with circles representing molecules of A and B. The black circles are molecules of chemical species B, which are produced in the red region. The green circles are molecules of chemical species A, which are produced everywhere. However, they are also removed from the system by this second-order reaction. So the red region, which has more molecules of B, will have less molecules of A. So this model shows that spatial pre-patterning according to chemical species B can lead to developing patterning in chemical species A. So this illustrative model could also be viewed as a model for pattern formation. In our last lecture, we presented the French flag model, which also required some pre-patterning. But there are also pattern-forming models which do not require any pre-patterning, like the Turing patterns studied in our last lecture. The compartment-based modeling has already highlighted the behavior of this reaction-diffusion system. So today, we will focus on the development of the corresponding molecule-based model. It is given as the SSA A18 to E18 on page 176. The first step implements a three-dimensional diffusion for each molecule. Since the system includes second-order reactions, we can no longer use a one-dimensional molecule-based model, because it is fundamentally different to implement second-order reactions in different dimensions. This is related to our discussion of diffusion to adsorbing surfaces in section 4.4, where we also showed that a three-dimensional model has different qualitative properties than the corresponding one-dimensional model. Degradation of A and B is implemented in step B18, using the same approach as in our previous example. For each molecule of A or B, we generate a random number R uniformly distributed in the interval 0, 1. If it is less than the probability of degradation, we remove the corresponding molecule from the system. The next step describes the production of molecules of chemical species A. Again, we use a random number R1 to check whether the production reaction occurred. Such an approach provides a restriction on the simulation time step delta t, because we want all these probabilities to be significantly smaller than 1. We will have further restrictions on the size of the time step delta t because of second-order reactions. They will often provide a computational bottleneck. All these steps could also be written using an event-based approach, calculating random times when the next event occurs, like we did with the Gillespie algorithm. You could think about developing an event-based algorithm as an exercise. The next step, D18, describes the localized production of molecules of chemical species B. We again use a random number to check whether the production event happens. If yes, then we introduce a new molecule of B to the red part of the computational domain. Finally, we implement bimolecular reactions. We implement these second-order reactions. The first reaction is the dimerization A plus A goes to a product, which we do not explicitly model. In our molecule-based algorithm, we postulate that this reaction can be described with the help of two parameters, reaction radius, ρ1, and reaction probability, p1. If the distance of two molecules of A is less than the reaction radius, ρ1, then we remove them from the system with probability p1. Similarly, the second-order reaction, A plus B goes to a product, is described with the help of two parameters, reaction radius ρ2 and reaction probability p2. If the distance of a molecule of A and a molecule of B is less than reaction radius ρ2, then we remove them from the system with probability p2. In our model, we know the reaction rate constants k1 and k2. If we want to use our molecule-based algorithm, then we have to specify the values of reaction radii ρ1 and ρ2 and reaction probabilities p1 and p2. This is discussed in detail in section 6.6. Once we know the values of reaction radii ρ1 and ρ2 and reaction probabilities p1 and p2, then it is relatively straightforward to write a computer code implementing our algorithm. The results of one realization of the SSA A18 to E18 are presented in figure 6.5, where we compare them with this black line, which is the solution of the system of deterministic partial differential equations, with the initial condition that concentrations A and B are identically equal to 0 at time t is equal to 0. As we already know, the deterministic partial differential equations do not exactly describe the average behavior of the reaction-diffusion system, because it includes some second-order chemical reactions. But the black line provides a reasonable approximation of it in this case. To visualize the results of our molecule-based model, we divide domain 0L into 40 bins and we plot the number of molecules in each bin at time t is equal to 200 minutes. This visualization enables a direct comparison with the results of the compartment-based approach, which we presented in figure 6.3, where one realization of the Gillespie stochastic simulation algorithm applied to the compartment-based model of the same reaction-diffusion system is presented. Considering the spatial histograms, the results calculated by one realization of the Gillespie algorithm are difficult to distinguish from the results calculated by our molecule-based model. We would need to calculate averages over many realizations to have a chance to see some differences. To conclude this lecture, let me mention a few words about section 6.6 on reaction radius and reaction probability. To apply our molecule-based model, we need to find a way how to calculate their values given the rate constant of the corresponding chemical reaction. For example, consider the reaction A plus B goes to a product. We have already seen this picture in section 4.4. Let us assume that this yellow ball is a molecule of A, and concentration C describes the concentration of molecules of B around this ball. If we decide that the reaction probability is equal to 1, then our molecule-based description of the second-order reaction is equivalent to adsorption to this sphere, which we studied in section 4.4, where radius R0 is equal to the reaction radius ρ2. In section 4.4, we calculated that the average number of molecules which are adsorbed per unit of time by this sphere is 4 pi times the diffusion constant d times the concentration far away from the sphere times the radius of the sphere. Therefore, given the concentration of molecules of B far away from the sphere, we know what is the rate of removal of molecules from the system by this adsorbing sphere. Comparing it with the rate of this chemical reaction, we immediately obtain the following formula for the reaction radius ρ2, which is equal to the reaction rate constant K2 divided by the sum of the diffusion constants of chemical species A and B. And we also have this factor of 4 pi coming from this formula. In particular, we could also use this relation to find ρ2 and postulate that probability P2 is equal to 1. However, this is not what I did in my illustrative simulations, and there are 2 sections of lecture notes dedicated to discussing the underlying reasons. So let me just briefly mention some of these issues. First, the reaction radius given by this formula is unrealistically small for typical values of rate constants K2 and diffusion coefficients. This is not so surprising from the biophysical point of view. If we assume that the reaction probability P2 is equal to 1, then we effectively postulate that every collision of molecules of A and B leads to a reaction. However, there are many non-reactive collisions, so in practice ρ2 should be much larger than what is given by this formula, and P2 should be smaller than 1 to get the same reaction rate constant K2. A small reaction radius also increases the computational intensity of our simulations, because we need to choose our time step delta t so that a typical displacement of a molecule during one time step is much smaller than the reaction radius. Otherwise, our simulations could be missing some collisions. Another issue is mentioned in section 6.7, where we discussed reversible reactions, like the reversible reaction A plus B goes to C and back. Considering the compartment-based model, there are no special issues with reversible reactions. We simply know that a reversible reaction is made of 2 chemical reactions, A plus B goes to C and C goes back to A plus B. Considering the molecular-based model, we could implement the first one using the corresponding reaction radius and reaction probability, while the reverse step is the first-order reaction. C breaks to form A and B. So we know how to calculate the probability that this reaction occurs during one time step. We also know that we can find the time when this reaction occurs using an exponentially distributed random number. The only problem is what we should do when this reaction actually occurs. We need to remove the corresponding molecule of C from the simulation, and we need to initialize the positions of new molecules of A and B. If we put them next to each other, then they will immediately react again, according to the reaction A plus B goes to C, because they are within the reaction radius. So we have to be a little careful here. More discussion of reversible reactions is included in section 6.7. This brings me to the end of lecture 17, which was our second and last lecture covering chapter 6, discussing stochastic modeling of reaction-diffusion processes. I explained the 2 main approaches, compartment-based modeling in lecture 16 and molecular-based modeling in lecture 17. We covered sections 6.1 and 6.2, studying a basic production degradation system with some applications to biological pattern formation in section 6.8. Our second example, covered in sections 6.3 and 6.5, highlighted many non-trivial issues because it included second-order reactions. You can read about these problems in the lecture notes in sections 6.4, 6.6, and 6.7, but please read at least pages 164 to 166 and 174 to 176 of the lecture notes, which cover sections 6.2 and 6.5, which we discussed today. This concludes our presentation of Chapter 6. In our next lecture, we will discuss Chapter 7. Again, we will only cover some selected sections. Thank you very much for listening to Lecture 17 of our course on stochastic modeling of biological processes. Bye-bye.